Hello students, today let's talk about the next chapter, that is the fourth chapter of inorganic chemistry, that is the D and F block elements. So first we will study about the introduction part of this chapter, that what are the D block elements. The D block elements are those in which the last electron enters the D subshell of penultimate shell. The general electronic configuration of these elements is this. It means the last electron enters into the D subshell, then S. So its electronic configuration just like N-1, D1 to 10, NS1 to 2, or NS2 we can write it, because the maximum of 2 electron by S orbital can be acquired, where N is the outermost shell. The D block consisting of groups 3 to 12 occupies the large middle section of the periodic table. For example, you have seen the periodic table. In the mid section you have seen that, just like in the 1 group, 2 group, and between 3 to the long group table from 3 to 12, we just find the elements in the middle section of the periodic table, that is D block, and the remaining are the P block elements. So in this series we will study about the transition element. These are also called transition element. D block elements are also called transition elements, and why these are called? The elements of D block are known as transition element as they possess properties that are transitional between the S and P block elements, because they show transition. These are also called transition elements because of the main reason. DD transition means the DD transition is just by the when the visible light passes through these D block elements orbitals, then the some part of the light is just observed and the remaining part is just splitting out from these orbitals, imparting the color. So these are the reason of their color transition effect, and this is due to the DD transition effect. A transition element is defined as the element which has incompletely filled d orbital and its ground state or any one of its oxidation states. These are also called transition elements because these are found in between S and P block elements, we can say that. And just because of DD transition effect, these are called D block elements. And now these have 4 transition series. First transition series, that is called 3D series, scandium to zinc. Second transition series is called 4D series, ytterbium 39Y2 48 cadmium. And third transition series are 5D series, lanthanum. So lanthanum is series name, and the elements actually start from lanthanoid from La57 to hafnium 72 HF its symbol, and hafnium 72 HF to mercury 80. So these are the series whose members first, these are the series of lanthanum where members start from hafnium 72 to mercury and lanthanium and lanthanoids. So fourth fourth transition series is the 6D series, begin with actinium and still it is considered as incomplete, so it is remain as it is in in periodic table. Now come to the point. Note some of the important facts. Note that zinc, cadmium, mercury are not regarded as transition element because of completely filled d orbitals, because the d orbital just like that, these are the d orbitals. So d 1 2 3 4 5 uh, 5 orbital of d subshell. So this has completely filled, this is a half filled, and it is completely filled. Just like if the situation is this, then then we says that it is it shows color and it consists of paramagnetic properties in magnetism. But if it is completely filled just like that, for example zinc 3D10 configuration, so its electronic configuration will be 1 2 3 4 5 1 by 1 according to Hund's rule or Aufbau principle, then fill in subsequent manner 1 by 1, 1 2 3 4 5 in this way. So 3D10 is completely electronic configuration, that's why these are not regarded as transition elements because of completely filled d orbital, so D10 configuration is uh, saying about it. So now come to the general characteristics of transition element. What are its general characteristics? First we will study about atomic radii. In atomic radii, the atomic radii of transition elements first decreases up to the middle. Up to the middle of the series, it decreases due to increase in effective nuclear charge and atomic number. After filling the d orbitals of half filled, then pairing starts in d orbital by the electron results in electronic repulsion, causing the increase in atomic radii from middle to the end of the series. So just like that, if we consider the 3D elements like scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So from the in this way till in the middle 1 2 3 4 5 6 7 8 9 10, in the middle section, just like chromium and manganese, its atomic radii first decreases, and then after completion of half filled orbital, this increase will start from this to zinc. So this is the reason of atomic radii of these d orbital first decreases and then increases. And after filling the d orbital half filled, then pairing start in d orbital by the electron result in electronic repulsion, causing the increase in atomic radii from middle to the end of the series. So this is the reason of increasing, because the pairing will start in starting position. If we look in starting position, the electronic configuration of d subshell will be like this, 1 2 3 4 5, and in some position first will be like this scandium, just like 1, then will increase up to 2, then will increase up to 3 4 5, and then the pairing will start in such a manner, then this first, and then start this, and then start this, and then start, and up to the zinc. On reaching the point zinc, this electronic configuration is completely filled, reason of increasing its atomic radii. So this is the simple concept on the basis of filling of orbitals. Now come to the next point, ionic radii. What is ionic radii? The ionic radii follow the same order as their atomic radii. In general, the ionic radii decreases with increase in oxidation state, because number of electron releases from their transition elements. Now come to the next point, what is ionization enthalpy? The ionization enthalpy of transition elements are higher than those of S block elements but lower than those of P block elements. It means if we have a look about its ionization enthalpy in this way, so we will find this thing like in this way. If we see the ionization enthalpy, just what is the fact is saying, the ionization enthalpy S block and P block element. This is the condition of periodic table. So if we see the periodic table in such a way, these are called the D block elements. The D block elements. These are S first group and second group. These are S, and these are P block elements. 13, 14, 15, 16, 17, 18, just like this. And these are called D block elements. So in D block elements, the condition is on here that the first ionization and enthalpy of transition elements are higher than those of S block elements but lower than those of P block elements. Means these are lie in the middle. Ionization enthalpy higher than S block element but lower than P block elements. S block element but lower than P block element. In such a way we can study the in a particular transition series, ionization enthalpy increases gradually with increase in atomic number. Means ionization enthalpy increase step by step very slowly with increase in atomic number due to increase in nuclear charge. Just it happens because of increase in atomic number, cause due to increase in nuclear charge. As nuclear charge increases, its ionization enthalpy increases slowly. By the increasing of d block electron in penultimate shell, electrons in penultimate shell, which provide screening effect and shield outer s electron from inward pull of nuclear charge. Means screening effect are the effect which counterbalance the outermost electrons, just like this. The first NSA until 5D transition elements are higher than those of 3D and 4D elements. This is due to greater effective nuclear charge acting on the outermost valence electron in this element because of the ineffective shielding of the nucleus by 4 electrons. So by 4f electrons. So one thing you have to consider in mind, this is the number of shell, this is the nucleus. So when the number of shells is just like increases and the shielding effect is just this, that these are not allowed to enter the electron in the inner word pool, in the inner shells. So if the poor shielding effect just because of largely distant and diffused, these are on very largely distant place, so ineffective shielding effect provides its nuclear charge attraction towards nucleus and causes by 4f electron. This is causes by 4f electrons, so its size is decreases, or we can say not effectively increases, means remains constant or some or slightly some decreases. So this is the reason. Now come to the next property, metallic character. All the transition elements are metallic in nature. They show gradual decrease in electropositive character in moving from left to right in a series. Means all transition elements are metallic in nature. This is the confirmed thing. They show gradual decrease in electropositive character in moving from left to right. If we move from scandium to zinc, from left to right, something is slowly decrease in electropositive character. The metallic bond are very strong in transition elements. In transition element, the metallic bonds are very strong due to greater effective nuclear charge, low ionization enthalpy, and large number of vacant orbitals. So vacant orbitals if are available, then bonding for bonding electrons are available, and this is the reason of very strong metallic character due to effective nuclear charge. So effective nuclear charge pulls the electron from its toward itself or to nearby the nucleus and causes of the remaining valence, the remaining orbital remains vacant of the reason behind it. Now come to the metallic melting and boiling point. Except zinc, cadmium and mercury, all the other transition elements generally have high melting and boiling point, because the zinc and cadmium have no unpaired electron. All d orbitals are completely filled. So these zinc, cadmium, mercury generally have high melting and boiling point, except these electrons, zinc, cadmium and mercury, because of completely filled d orbitals. uh, uh, Besides these elements, all the other remaining transition elements generally have high melting and boiling point. This is due to strong metallic bond. And why it is happens strong metallic bond? Due to presence of unpaired electron, or this thing is written on here, presence of partially filled d orbital, and causes some covalent bond also exist in between atoms of transition elements. So now come to the next point. uh, in the due to covalent bond. So this has happened due to covalent bond, and partially filled d orbitals are the main reason for it. Now come to the next point in the note section. This important note: in moving along the transition series from left to right, the melting point first increases up to middle and then decreases. Melting point first increases and then decreases because all uh, because from mid the electrons are paired up in d orbitals. So this is the reason. And when the electrons are in the process of pairing, so after the pairing, so when the electrons are going to paired, and its melting point decreases because of pairing of electron and d orbitals. Now come to the next point, oxidation state. What are the oxidation state? All transition elements show variable oxidation state due to participation of ns and n minus 1d orbitals. As we know that vanadium shows +1, scandium +2, and orbitals just like +1 +1 +2 +3. Next is +1 +2 +3 +4 up to the middle. This is the maximum oxidation states shown by transition elements. But after its so in this transition, n the s orbital electron and n minus d orbital electron participation is very actively occur. So this is the reason of its variable oxidation state shown by transition elements. Now come to the next point, standard electrode potential. This is represented by E naught, and generally we study in electrochemistry part also. Electrode potential is the electric potential developed on a metal electrode when it is in equilibrium with a solution of its own ions, means taking electrons from the electrode. So in galvanic cell we will just study about in two half cells. The metal electrode plates are used in two half cells, and we see that electrons are moving from one metal to another, and and creating a potential difference between them. So this is the reason of standard electrode potential, because electron transference process are takes place in it. So the electrode potential decreases up to the middle of the series due to the half filled orbital. This is the same reason of this up to the middle. All the reason are interlinked with the same process. Up to the middle of the series element, just like chromium, the electrons are in the process of filling the orbitals. It means up to the half portion of the series the electrons are not paired, but after half portion the electrons are starting pairing up. Reason for the electrode potential decrease up to the middle due to half filled orbital, and increase the end of the series due to increase in number of electrons. As the number of electrons increases, the electron potential increases from the middle, and from starting to the middle it is decreases. So this is the reason behind that. Now come to the magnetic properties. Now come to the magnetic property. Substances containing unpaired electron and said to be paramagnetic and diamagnetic substance is one in which all the electrons are paired. If in the d orbitals, like just this is the 5 orbital in the subshell, if electrons are in this way, then it is a paramagnetic. It is paramagnetic and it is also paramagnetic. But if the pairing is completely done, then it is called diamagnetic. So this is the process of magnetic behavior, and this is can be in magnetic moment. Regarding this magnetic property can be calculated by number of unpaired electron. N is the number of unpaired electron. Here is the 0 unpaired electron, so its magnetic moment is 0. But if it still have one electron, then on putting the value of 1, and 1 plus 2 is 3, and 3 ones are 3, so under root 3 1.732 may be the magnetic moment, which is measured in bar magneton. So in this way we can easily calculate the magnetic moment. If it is a 2 electron any d orbital, then it can have on putting the value of 2. So 2 plus 2 4, 4 to the 8, and under root 8 we can easily calculate, and under root 5, under root 35, easily we can calculate the magnetic moment according to the number of unpaired electrons. Now come to the complex formation. How it is complex formation takes place? It is due to high charge on transition metal ions and the availability of d orbital for accommodating electrons donated by the ligand's atom. It means why is the complex formed in the d orbit in the transition elements? It is due to the high charge. First is an high charge on transition elements ion, or availability of d orbital for accommodating electron donated by the ligands. It means just like this, the availability of d orbitals in such a way in the section that their 4s orbital is just like this, 4s 3d, and it's the 4p orbital in any complex ion we just see. So the availability of d electron, when any ligand donates its electron, so it has completely availability of d orbitals just like this. And after it the vacant orbital is also there if these are all are paired by the strong field ligands. So 4p 4s and 4d orbitals just like this are also available for bonding. So this is the reason of complex formation: high charge on transition metal ions or availability of d orbitals for accommodating electron donated by the ligand. For example, NHCO NH3 whole 6, 3 positive, this is the complex. And we just see that 2 positive we can see, or 3 positive we can also take. So this is the complex. Here the number of ligands are the amines. So amines are filled up in all the required d orbitals according to its suitable condition. So this is the reason for the complex formation of transition elements. Now come to the next part, color. I have also told that if the one electron or two unpaired electrons are found in a complex, then it shows color. Most of the transition elements are shown solution as well as solid state are colored due to partially filled. Here point to be noted, due to partially filled d orbitals through which visible light passes. This is the reason I have explained in a very starting, and passes and absorb, which is further emit into respective colors of the particular transition metal by dd transition. Now the next point is alloy formation. Alloy are the compounds we know very well, which are formed by the metal and non-metal mixture. So the transition metals, now point is this, so why transition elements actively form alloys. So the reason behind that are written on here. The transition metals have similar radii and other characteristics. Therefore, these metals can mutually substitute their position in their crystal lattice and form alloys. These are hard and having high melting and boiling point. In a crystal lattice, just like a chapter of solid state which are deducted, but its application is on here. Just like we see that the crystal lattice structure is like this. So this is the crystal lattice structure in which the electrons, the vacant side are these are the electron, positive and negative anions. So these are lattice sites, and therefore these metal can mutually substitute their position in there. So in this metal sites, these are substituent their position of the metal, like we can take any metal XYZ can be substituted on any position, either on this position easily. So this is the reason of alloy formation. And why it is mainly happen, just because of similar radii and other characteristics as mentioned above. So now come to the next point, interstitial compounds formed by transition element. Interstitial compounds are those in which small atoms occupy the interstitial sites in the crystal lattice. Interstitial compounds are well known for transition metals because of small size atom of hydrogen, boron, carbon, nitrogen. Means these are the interstitial side I have explained. So these can be occupied, small atoms occupy the interstitial sites in the crystal atom. Interstitial compound are well known for transition because of small size of atoms of hydrogen, boron, carbon, nitrogen can easily occupy position in the void present in the crystal lattice. This is the transition element crystal lattice structure. If the any interstitial sites are these vacant sites, if occupied by one of these elements of hydrogen, boron, carbon and nitrogen occupy easily. So this is the reason also for alloy formation and also for interstitial compounds in transition elements by the study of these crystal structure. So in this way we just study about the main property of transition elements. Now let's talk about the previous year question of the CBSE examination is asked. So the question is just like that, account for the following transition metals to variable oxidation states. We have discussed earlier about it. Transition elements show variable oxidation state because of the participation of s electrons and n-1 d orbitals electrons are available for bond formation of nearly same energy. Why these both are actively available? Because of these have very nearly energy, just like very close energy, so can jump to occupy the subshells of d orbitals. So this is the reason of the transition metal show variable oxidation state. Now the question is, zinc, cadmium and mercury are soft metals. These are, so I have also discussed earlier about it, that because these have fully filled d orbital, absence of unpaired electrons cause weak metallic bonding, hence they are soft. So these are the soft because of absence of unpaired electron. Generally transition elements are hard, but because of d orbital is completely filled, these are soft. These are the exception in transition elements. So now next question, E naught value for the manganese Mn3 positive to Mn2 positive couple is highly positive. These have electrode potential just like plus 1.57 volt as compared to chromium Cr3 positive to Cr2 positive. So this reason is much large third ionization energy of manganese, where the required change is stable half filled D5 to D4. Why it is happened? Because manganese have fixed 3D5 stable half filled electron configuration, so it is hard to take out from its stable electron configuration to unstable. So d on converting from d5 to d4, it's very typical, it's very hard because half filled are very stable. So this is the main reason for the E naught value couple is higher of manganese ions as compared to chromium ions. So now come to the point. Next question. So next question is, account for the following. So transition metals form large number of complex compounds. Why they form large number of complex compound? Small size and high charge density. This question has come in CBSE Delhi 2017. Its answer is, so we have to write as short as possible as with the direct accurate result, not in a too descriptive manner. We just ask thoroughly the exact answer of the asked question. So small size and high charge density on metal ion and availability of d orbitals for bonding with ligands. So small size and high charge the reason, and availability of d orbital, as I have shown by drawing the d orbital structure, that how they are available for bond formation with ligands. So this is the reason of transition metal form large number of complex compound. Now the next question is, the lowest oxide is basic whereas highest oxide is amphoteric or acidic. The reason behind that, lowest oxide of some metal, in lowest oxidation state, some of the valence electrons are not involved in bonding and can donate electrons to the other, whereas in highest oxidation state, valence electrons are involved in bonding and accept electrons behave like an behave like an acid. So the clear reason is, we have to remember one thing, that in lowest oxidation state, valence electrons are not involved in bonding. Simple, not involved in bonding, valence electrons. And in in highest oxidation state, valence electrons are involved in bonding and accept electron and behave like an acid. So these things we have to remember. In lowest oxidation state, valence electrons are not involved in bonding, but in highest oxidation state, this involved in bonding and readily accept the electron. And by the Lewis theory, we know that those compound which accept electrons are treated as an acidic compound. So now come to the next previous question in this series, that E naught value for the Mn3 positive to Mn2 positive is highly positive as compared to Cr3 to Cr2 positive. Why it is happened? Much larger third ionization enthalpy of manganese, because I have told you earlier that T5 is the stable electronic configuration, because one electron in each orbital, that is called half filled, because each orbital is singly filled electrons. So this is mainly responsible for this. Whereas chromium electronic configuration is 3d5 4s1. After removing 3 electron, its electronic configuration will be 1 from s orbitals and 2 from d orbitals. So these will be 3d3. So 3d3 to Cr2, so 3d3 has half filled, but this is very stable, it's all have half filled. So manganese is the much larger third ionization energy required, change is stable half filled is mainly responsible for this, because converting from d5 to d4 is very hard. Now come to the next question, write one similarity and one difference between, this is the question. So these are some important question we have discussed about the E naught value, standard reduction value. standard reduction potential value. Now come to the next question, that is account for the following: Mn2 positive is more stable than Fe3 positive. Same reason, because 3d5 electronic configuration half filled, which is more stable as compared to 3d6. Next, the ionization enthalpy. The enthalpy of atomization is lowest in zinc in 3d series of transition element. This is because of the completely filled d orbitals is completely filled. The 3d subshell is completely filled and no electron is present for middle bonding in zinc in 3d series of transition element. So these were some questions which are very important from examination point of view, as you can prepare these question by on the basis of the property of transition elements. So if you like this video, please comment, like the like and subscribe the channel. Thank you.